Well, so today we will discuss some of the issues related to the digital architecture design in VLSI and whatever the trend today the technology is going, and depending on that, some of the issues which earlier were not at all looked after in the design. So, what are the impacts of them in today's design and possibly in some future design. Okay, so let me start with very basic that I think you are already having some idea that how it is integrated within silicon, but still just for the sake of completeness, say you have got a transistor. So, how do we used to depict that? Suppose this is a region N, there is another region say P, there is another region N, and maybe their doping concentrations are different. So, you know that this is emitter, this is base, this is collector. Okay. Now, you have to integrate so many transistors into a small microchip, maybe the dimension, the typical dimension is less than 1 centimeter by 1 centimeter. So, how do you miniaturize this? The process is basically, I mean whatever we are going to discuss is the silicon process. So, those who are already aware of the device fabrication technology, so maybe a little bit of silicon process you already know, but once again just say we start with a circular disc of very pure silicon. Very pure means it is electronically, I think you are aware of how much pure it should be, because otherwise what will happen, if the contaminants are there, then your required or desired electrical property you will not be able to achieve. So, on that circular lamina, maybe this is somewhat it depends on the technology actually, it might be as small as say 2.5 inch in dia or maybe as large as 8 inch dia. Now, if you think about a small chip, it will be just a small part in that. So, in one so called silicon wafer, this is called a wafer, you may fabricate more than 100 of such microchip in a single go, and typically you use the same chip, you repeat it over the whole wafer. So, if you take the top view of that one, then you may find that there are several chips lined up like this, but now how do you actually fabricate this? So, let us begin with that NPN transistor, how you can fabricate this. So, I am just using a cross section of the same thing, maybe not to the scale, a little bit exaggerated, so that we can understand this. So, this is from the side if you look at this. Now, we grow a silicon dioxide layer on top of this silicon by exposing the silicon wafer on a high temperature oxygen environment. Now, that oxygen has to be also very pure, otherwise if there is some contaminant, then desired electrical property will not be achieved. So, now this is the oxide layer and this is the silicon. Now, you can etch out some window, that is if you look from the top, then maybe a small window you will find over here that you can etch out on the silicon dioxide and expose that to some sort of dopant gas. N type means what is the typical dopant? That is phosphorus. Okay. Similarly, P type may be boron. So, if you want to have some sort of N type island over here, you expose a part over here and you allow the dopant to get diffused into that. As a result, what will happen? There will be some N island formed over here. Okay. Now, depending on the doping concentration, the time, temperature, what will be the depth of the junction that you can determine. Similarly, if you open windows simultaneously while you are exposing that to N type dopant, you can have many number of such N islands. So, in your design, suppose there are millions of transistors. So, in one go you can have millions of such islands made. Now, you need to have some sort of P region. Okay. So, within this maybe once again I can exaggerate this one. Suppose this is the N island whatever you have made, and once again you cover it up with silicon dioxide, then expose some of the part, once again open an window So I think you know hydrofluoric acid or some such material that can etch out silicon dioxide. So in the same way, you can etch out a window, expose that to some p-type dopant, then you can form some p-type structure over here, not p plus, p-type material you can diffuse. Once again you etch out the whole oxide, grow another level of silicon dioxide, and maybe use a smaller window like that. Through that you can diffuse once again some N region. Okay, so maybe its doping is much more. I mean generally we use N plus here and N here. So now you see this is an NPN type of structure. Now you need to use some sort of contact over that. Okay, so once again you cover it up completely with silicon dioxide, etch out some contact window, and after that contact window it would look something like this. One contact will come from here, a vertical structure having metal touching this N region, one will be here touching the so called emitter region. So now this is your emitter region, this is base region, this is collector region, and you have to make this base region thin, which may be not properly scaled in this drawing, but you have to control all the parameters like doping concentration, temperature, etc., so that you require, I mean you can achieve the required height of the junction or the depth of the junction. Okay, so now this connection, this will be the emitter connection, this connection, all whatever I am drawing in black is metal, this is collector. Okay, so in that way you can make a bipolar junction transistor. But nowadays the digital technology, they are mostly using so called CMOS logic. So what is CMOS logic? You are using MOS transistors for its fabrication. So why you are using MOS transistor? I think some of you are already aware that MOS transistor, they are consuming much less power. Okay, so what is the reason? Reason being the circuit, whatever the topology, that is such that the short circuit current is almost 0. Okay, so I think mostly you are aware, but still we can just look at one such circuit. The simplest possible circuit is the circuit of an inverter. So the top one, I mean there are numerous symbols used in various literature. For digital structure I am using this. Okay, so this is p-type MOS and this is n-type MOS. Now the circuit is something like this. Here you connect that to positive power supply, and here whatever is the negative most or the ground, and the inputs are tied together. We provide the input over here. So if we call that input point A, then we can take the output from point Y. So now how it works? If we think about an n-type transistor, and if we look at its structure, I am once again just drawing the schematic of that. This will be the source or drain, and this will be the other terminal, that if the first one is source, the other one will be drain, and this is once again silicon dioxide. Here the thickness is much smaller, much less. Now over that we put something called a gate. This is I think very much familiar structure, and here once again you open a contact window over which you can put some metal. Here also you can put some contact window, you can put some metal. This is the so called gate terminal, maybe this we will call drain, this we will call source. So whenever we are applying say a positive potential here with respect to the source or the substrate, then since substrate is P, the minority carriers are the electrons, they will get attracted towards gate, and as a result they will be flooding the channel over here. I mean so called the channel is formed, and the electrons will start flowing from source to drain, provided that you have got some potential difference between them, and if this is positive then it will try to attract the electrons. So as a result some current will flow. So in other words, if we make gate positive with respect to source, we can turn on this switch, otherwise it will remain turned off. So the logic for p-type transistor will be just reverse. So now what is happening when we are applying a logic 0 over here, that is a lower potential, lower means maybe it is equal to the ground potential, then if I look at the p-type transistor, then here having a lower potential, just in the same logic it will be having a channel made up of holes, and this transistor will become on, and here we will get a logic high because now VDD is being communicated to the output. Consider the other situation when it is changing from 0 to 1. Now at that time this is turning off because now this is at high potential, this also we are making at high potential, but here this side the source is at 0 or ground potential, here we are giving a positive potential, so the channel is formed, the current can flow in this. So now this output Y is connected virtually to the ground, keeping this value low. So from high it will be low. So we used to draw something called a truth table and say that if A is 0, Y is 1, if A is 1, Y is 0. Okay, and maybe we can draw a symbol that this is an inverter. So far so good. But in VLSI, whenever we are integrating that, we are making such transistors over there, then there are several issues coming up. First of all, we have mentioned that this type of device, or rather this type of topology, they consume very less power. Okay, but how to calculate the power consumption first of all? If we know that okay, 10 such inverters are being made, all are having similar topology, maybe the transistor sizes they are slightly different, or the doping concentration they are slightly different, but we need to find out what is the power consumption. Whatever we have discussed so far is just related to its functionality. Okay, so digital, I mean sometimes we treat it as just something which deals with logic 0 and logic 1. So it is not really that, particularly when we are talking about digital VLSI. Then we need to calculate power consumption. So if we just think about the power consumed by this inverter, so how do we proceed? We have to find out that what are the mechanism by which one transistor is coming from an on state to off state or off state to on state. And sometime we will find, I mean if we really track this change, then we will find that the resistance of both the switches, if we can plot with time, suppose at this time the change at the input has occurred. Till that time one of the transistor, let us say P transistor, this is having very low resistance. Okay, maybe its resistance is something like this. So now as soon as it is changed, it tries to become off, so its resistance is increasing. So in some normalized scale we can say that it has attained the maximum possible resistance. Now what about the other transistor? The other transistor initially it was off, that means it is having some very high resistance. So this resistance and this resistance may not be identical, just I am drawing in some normalized scale. So now just after that moment it tries to become on, so finally it will reach a small resistance. So here I am plotting R on of both the resistance of both the transistor. The green one is P type and the blue one is sorry, it's the other way around, I think. This one initially we are thinking it is 0, so N type is off. Okay, so this is N type and this is P type. So now what we find, at some portion of time both of them they are moderately conducting. Okay, so as a result what will happen, there will be some current flowing from the power supply directly through two transistors to the ground. So if we look at the current waveform, then we will find that the current, maybe here it is 0, here also it is 0, in between there will be a current pulse. Okay, so red one is the current drawn from the power supply, so it will be having some peak. Okay, now there is another issue. In this case we are assuming that the transition is instantaneous at the input. That might not also become true. If we look at a very high resolution oscilloscope, then we will see that actually the waveform might be something like this. It has got some finite or rather non-zero rise time. If I look at the input waveform, so from this point to this point what is happening? It is not exactly at 0, it is neither at 1. So for that portion of time both the transistors might conduct, I mean whatever we have seen, this is not only due to their inherent delay but due to the rise time of the input signal. So if rise time is more, that means it will get more time to pass the current through both the transistors. Okay, so power consumption will be more. So depending on various situations you can find out the power, you can reduce that, but anyway when it is really not working, that is it is at the steady state 0 or 1, at that time the leakage current is minimal. But there is another current which is I mean substantial, that is the output is obviously driving some other components, maybe some other gate. Okay, so now gate has got two meaning, one is the logical gate we are talking about, and at the same time it means gate of the other transistor. So now whenever we are talking about gate of the other transistor, it is basically forming a capacitance. There are two parallel plates, one is metal, but however in today's technology we don't use metal, it is polysilicon now. So it is a parallel plate capacitor. So effectively the output of an inverter or any other gate, so to say, is finding a capacitive load connected at its output. So even if we consider that this short circuit current is pretty small, but what will happen due to the current, I mean that can pass when the P transistor is on, this current will charge up this capacitor, right. Now in the next cycle when N transistor will become on, this capacitor will discharge through N transistor. So there will be power loss in one full cycle. You can calculate how much will be that depending on the value of the power supply, the load, and in I mean how many times you are doing this in 1 second. If you know the clock frequency and if you know something called an activity factor, that it is not necessary that in every clock cycle it will change its state. But if you know that in 1 second how many times it is changing their state, then you know in how many cycles, I mean in how many times in 1 second it is getting charged and discharged. Okay, so that is called dynamic power dissipation. So all this that will come into the picture whenever you are designing a digital system, particularly in VLSI. Now let me just have an hierarchical view of that. Some designers, I mean if we think about VLSI design flow, some designers they are working at maybe the design of a very complex processor. Okay, so it is not possible for them to know each and every detail at the manufacturing or fabrication level. Okay, but as we find that without that knowledge also it is not possible to optimize the whole flow. Okay, so what is required is that if we can identify that what will be a person's job when one designs a VLSI circuit, then we can identify, and then at various levels we can find out that what are the interaction of the knowledge required. What I want to mean is that suppose one who is designing a processor has to deal with I think you are aware that the microprocessor chip that is inside the computer, there are several instructions for that. So what will be those instructions, how the instructions will be executed. So maybe one engineer is just devoting his or her time for that. So he or she need not know each and every detail at the manufacturing or fabrication level, but at least should have some idea that okay, what will be the impact of a change at the top level. Okay, so let us look at the VLSI design flow. So at the top level, if we think about that, it is the specification that we start with. So specification is something which says that we want to design a chip, what should be its purpose. Okay, so that will be something you can say an architecture, an algorithmic level description. So here maybe I am having some sort of algorithm by which I am specifying that the chip should be able to follow this path for deciding something. So it should have some definite rule that given an input specification, it will be able to unambiguously decide what will be the output. Now after the specification, when it comes to the VLSI designers domain, they will try to form something called an architecture out of it. Okay, so from the specification we will try to find out some architecture. So architecture will be basically a block diagram containing maybe registers, counters, something like this, and in VLSI parlance it is called an RTL description or a register transfer level description. Okay, so what is that? In an algorithm you are talking about various variables. Suppose you say that y will be equal to a plus b. Okay, So an algorithm specifies that. Now in architecture, we will be finding out that okay, these are several variables we need to deal with. So how do we store these variables first of all? So I think if you are aware what is a flip-flop, you know what is a flip-flop? So a flip-flop can store 1 bit. So if you can put several flip-flops, maybe 8 flip-flops, then you can have 2 to the power 8 possible combination. One flip-flop can have any any possible combination out of 2. So if you consider them to be independent of one another, then you can have 2 to the power 8 combination stored in an assembly of 8 flip-flops. So we call them a register. The name is obvious that it can register a variable whose value is maybe starting from 0 to 255. 255 is the maximum value that you can, and I think you are aware of that, how to represent negative values, etc. Now depending on the value of the variable that you have to handle, you can decide the size of the register, that how many flip-flops you will be putting. If you require higher values, maybe say you can put 16 flip-flops, then the maximum is 2 to the power 16 minus 1, that is 65536 minus 1. Okay, so something like that. So here, if we once again come back to that architecture at the RTL level, we will be putting some registers, maybe one is A, another is B, that will store the values of A and B, which are known. Whatever I am writing in the right hand side, they are known, and we want to find out the variable at the left hand side. Now we need to identify that what is the operation involved. So here the operation involved is an addition. It could be something else also, but right now it's an addition. So operation is add. So we have to put some hardware block which is capable of adding two numbers. So if we call that an adder, so there will be a hardware block which we will refer to as an adder, whose two inputs will be connected to the two registers, and whose output we will put another register, and that register will be called Y. Okay. So I think you are aware of this Boolean algebra, that how to add two numbers and in that binary logic. Okay, so using that we can form some adder and then we can put it over here. So that we will say it is something called register transfer level, because what are the various registers we require and what are the transactions between various registers involving the combinatorial element. So why we are calling this adder a combinatorial element? Because the output of an adder, it is solely dependent on the input patterns. Whatever is the input pattern, depending on that it can decide unambiguously what will be the output. Okay. Now if we contrast that to so called sequential element, then we will find that in sequential element there is a bit of memory. Okay. So depending on that it will decide what will be the output. It is not solely the inputs that can decide the output. So we will come shortly to that sequential logic, but let me complete that. So after architecture, what we require, here we have drawn something, say just a black box saying what is its functionality, but how do you realize that? As we have already mentioned that maybe you can put flip-flops over there. So here at the architecture level there are some functional blocks. So if you try to break them up into smaller functional modules, that we will call something called a logic design. So logic design involves the detailed design of this functional units, whatever we have already referred in the architectural design. Okay. Now this adder, for example, this will be requiring several gates, maybe XOR gate, AND gate, OR gate, for realization of sum, carries, etc. So this design also will be coming under the purview of the logic design. So logic design, it basically deals with the design at the gate level. So gate doesn't simply mean AND gate, NAND gate, but maybe it can include some of the higher functional entity such as a multiplexer, flip-flop, whose design is already phrased or is well known, so that we can consider that to be a single functional unit like a gate. Okay. Now after the logic design, where we have come down to more or less a gate level, then what will be the next step? That gates are to be realized using transistors, right? So the next step would be circuit design. So after logic, that should be circuit design. Now circuit design means we are talking about transistor level. Okay, so here we are talking about how do you realize those gates. Maybe it's an AND gate, but as you are aware that there are several technologies, CMOS, then something called TTL that uses bipolar junction transistors. So how do you actually realize those gates using transistors? Okay. So now maybe the same gate in two different technology, in one case you are realizing with a MOS, in another case you are realizing with BJT. So their performances will also differ, right? Now after circuit design, what is left out then? Because at the circuit level you have already reached something like a transistor where you are using either this or maybe something like this. Okay. So the next will be the device, whatever we have drawn earlier, that what will be the device geometry, what will be the doping concentration, etc. So after circuit design, basically you are entering a domain which is called physical design. So up to this portion sometimes is called the logical design, vis-a-vis physical design below that. So a physical design talks about the geometric layout, the actual doping concentration. So here it is basically device design followed by the layout. So why do you require layout? Because how do you fabricate those masks that will allow you to open windows in the silicon dioxide and to create all these islands, etc. So after that actual fabrication process will follow. So design of layout and fabrication. So I am not elaborating the scope right now. So I am simply writing layout and fabrication. After fabrication, obviously we require to test that and package it. Okay, before package maybe we have to throw away some chips also. Okay. So now if you look at the various levels whatever we have described so far, so starting from specification, as you can see there are several steps which will take us to the finally packaged chip. Okay. So it is not possible for an algorithm designer to understand all the basics of a transistor level design, but what will be the impact that should be known. Okay. And we will see that it is possible that at every level we can have some sort of optimization. Okay. So let us look at this, that what do we mean by optimization at various levels. Say specification, we have mentioned that it is something like an algorithm. So say the problem says it is summation of n natural numbers. Okay. So we have to have sum of all natural numbers up to some user given value, say n. Okay. Now how do you use this? So if we know that there is a closed form for finding out this, then we can reduce the computation drastically. Otherwise we have to keep on adding up to n. So there will be n minus 1 additions involved. Okay. So what is that formula? So directly if we can write down that closed form, n into n plus 1 divided by 2. So now we find that it is getting reduced to just a single multiplication and one increment operation. Okay. Increment is actually economic compared to a simple addition, because in addition you can change both the variables at your wish, but here it is a fixed one. So if you look at the hardware, it is quite reduced. And division by 2, in binary it is nothing but a shift of the point. Okay. In decimal if you shift the point, it is divided by 10. So in binary if you shift the point, so you really require any hardware. Okay. Whatever the lines are coming out, if you just change their definition, it will be automatically having a scale by a factor of 2. Now suppose this optimization which you can do at the algorithmic level, they need not know anything about electronics, right? So it is at the level of algorithm designer this optimization is possible. We will call it algorithmic level optimization. But now it is also not possible for an architectural designer that who will be picking it up at the next level to know about all such optimization. Maybe it is a very simple thing which is known to all of us. That is why we can say that, okay, rather than having a series summation, we can use this formula directly. Otherwise, whatever the algorithm designers are giving us, we have to rely on that. Okay, we assume that they are expert in that field and they are supplying us with that algorithm. Now, so far as the architecture design is concerned, just for the sake of argument, let us say we are not aware that such a thing exists and we are working on this. Maybe some inefficient algorithm designer, you can say, they have told us that okay, this is the kind of stuff we have to do, and maybe it is given that okay, the algorithm looks something like this, that input from the user the value of n, then we need to initialize the variable say s, then for I equal to 1 to n we have to add up this number like this, s equal to s plus I, and then we have to increase the value of I. So I will take the next value, go back here until it is reaching n, and if it is found, then we can output the value of s. Okay, so that ends the routine. So being unaware that there is a closed loop formula like this, let us say we the architectural designer, we started to map this into an hardware. So then how will it look like? First of all, we have to identify the number of variables, that how many different variables are there. We find n, s and I, 3 variables are there. So we will put 3 registers in our circuit, and at the same time we have to find out that what are the combinatorial blocks required for any arithmetic or logical operation. So here we find it is this one, that is the addition operation, right? So if we just try to map this one into an hardware, so how will it look like? First of all, there will be a register which we may call n, where the user will be putting the final value, and what are the other registers we require? One will be s, one will be I. So I actually, rather than using a simple register, what we can use, if we look at the scope of I is changing from 1 to n always. So rather than using a simple register, we can use a counter which will start count maybe from 0, because even if we write down I equal to 0 to n, the algorithm, I mean the output will not change. Okay. Now what is the logical operation or arithmetic operation involved over here? That is addition. So we will require an adder over here, just the whatever we have drawn earlier. So s and I need to be added. So where the result will go? S. So it should go back to s. Okay, so that completes the structure. So this portion we will call a data path, because data is flowing through this, and final output will be obtained from the output of s. Now how n will be coming into the picture? Because we have to stop this computation of this loop. So who will do that? There will be some block called a comparator that can find out the relative values at its 2 inputs. Okay. So suppose the input, if I call it x and y, the output will become high if x is less than y. As long as x is less than y, let us say this output is high. So we will call this block a comparator. It's a simple digital structure. Now the output of comparator, how we can use? Because at every clock cycle the counter is counting, and at every clock cycle the register is getting modified. So that will, I mean, we should run that as long as n is greater than or equal to I. Okay. So maybe if we connect something like this, which will enable this register as well as it will enable this counter, that as long as this is more than this, it should be enabled. Okay. So then what will happen? When I is equal to n, okay, so then possibly it will not give proper output. So maybe we have to include that equal option also here, that as long as it is greater than or equal to, then you keep this thing on. So now when I is more than n plus 1, then what will happen? They are already low, so it should not be updated. So in that way we can map one algorithm into an architecture. Okay. So now there are several issues. For example, you can find out what will be the area, we can find out what is the maximum speed. So how do you find out what will be the speed? Because in this case the speed means how quickly we can achieve the result. So here, because we are simply adding it up, it requires n minus 1 cycles for addition. So after n cycles we should be able to get the result at this point. At S, if we take out that, we should get the result. But now how quickly it can be done? If we look at the output of say I or S, then we find that the output is changing only at a clock edge. So what is clock? Clock is a signal which is something like a square wave that is giving some sort of indication of time, and all the counters, registers, they are designed in such a way so as to respond with some sort of clock edge, either the rising clock edge or maybe the falling clock edge. So I am assuming rising clock edge. So if the value of I, that is the counter, is 0 before this clock edge, so first one is clock, second one let us say is value of I. So if it is 0 before the clock edge, after the clock edge it should be 1, after this clock edge it should be 2, after this clock edge it should be 3, 4 and so on. Okay. Similarly, if we have initialized S with 0, then S value is also 0 over here, and now we are adding I and S by means of this adder. So its output is also 0, so that will come back to the S itself. So 0 plus 0, 0 will come back here itself and it will be latched in the next clock edge. Now it will be 0 and 1 that will be added up, and the result, that is 1, will be latched in S in the next clock edge. So in that way the computation will progress. Now 2 and 1, that is the values of, these are the values of 1 and I and S, result is 3. So 3 will be stored in S and so on, 3 plus 3 is 6. So in that way the computation will progress. Now depending on the actual internal circuit inside this, I think some of you are already aware that XOR gates, AND gate, OR gates, they are I mean here to realize this adder functionality. So they are having some propagation delay. It is not that if you allow the input to change instantaneously the output will change. It will take some time. So what is that time, that will decide what will be the maximum speed of this. If the gates are faster, so what do we mean by faster gate? If you refer to our earlier diagram that we have drawn at that time, that this one. So how quickly the capacitor can discharge through this. So this involves the load capacitance value as well as the resistance of the P channel or the N channel transistors. If resistance is high, it will take more time to discharge. Okay. Similarly, if capacitance is high, once again it will take more time to discharge. So now if it can discharge very quickly, then we can have quite high speed, but however it depends on the actual technology. We do not have much control on that at this higher level, that is the architectural level. But if we know that this is the time, let us assume that it takes 1 nanosecond to complete one such addition. Okay. So then whenever the S value is changing, say at this clock edge it is becoming 0 to 1, now the adder will take 1 nanosecond to add up this 2 and 1 and produce the result 3. So unless that 3 is presented before the register, it cannot be latched properly. So before 1 nanosecond, if the clock edge occurs, it will perhaps latch some erroneous result. Okay. So now the delay of this adder or the combinatorial block, that will decide what is the maximum possible speed in this circumstance. And for a large design, it will be the slowest combinatorial block that will decide what is the speed, and in that case it will be called the critical path. So critical path is the longest combinatorial path, longest in terms of delay. Okay. So it is the combinatorial path having longest delay between two registers. Okay, that decides the maximum speed. Now we see what optimization is possible at this point. First of all, look at the usage of the hardware, whether any extra hardware is used over here which is not really required. Apparently not, because whatever the number of variables, we have simply mapped that, we have not put any extra variable. Okay. And sometimes we find that some of the variables they are short lived, say they are only present in the first half of the algorithm, that generally happens in a very long or complex algorithm, but here the algorithm is also very short. So there is no such scope that one variable is utilized only in the first part and some other variable is utilized in the second part, which is not there in the first part. Then possibly we could have shared one register for storing two variables at two different times, but here that is also not possible. Okay, so apparently this is already optimized, but if you look at their utilization, whether they are utilized 100% of time, just let us have a check. What about this counter? It is changing its state in every clock cycle. So it is, I mean, quite well utilized, we can say. Similarly, this one also, in every clock cycle, the register S is getting updated. Okay. Now, what about the adder? It is adding in every cycle, it is getting different data, so it is also working. What about this register N and comparator? The N we are loading only during the time of the input, it is not changing in the whole course of computation. Only when you go for another computation, then its value is getting changed. Similarly, the comparator, though it I mean keeps on comparing, but finally it results, I mean it is just having one result. Its result will flip only when we find that I is becoming greater than N. So most of the time we find that at least this one is lying idle, no doubt about that. Okay, but can we get rid of this? What is the problem if we simply eliminate this? Yes, so it will not stop at the desired location. So we can just see once again at the algorithm that what we are trying to achieve. We are trying to add all these numbers. So is it necessary that we have to first start from 1 then add 2? That the order of computation should be from this side. What if we start from the opposite side? If we start from n, okay, then reduce the number to n minus 1, then always we have to stop at 1 or at 0, doesn't matter. Okay, then what is the change at the algorithm that we have to bring? So rather than saying 1 to n, here we can say I equal to n down to 1. We can make that change. So for a complex algorithm, maybe we once need to get back to the algorithm designer. We have to say that look, if we change the order of the computation, whether it matters, because if it is a very complex algorithm, it might not be possible for a VLSI designer to analyze each and every detail involved in that algorithm, and maybe there is some component, if we change the order of that one, maybe some transformation is required there also. Okay, so once, at least for this example, we are satisfied that even if we change the order, the output will remain same. So now what is the modification in the architecture that we can think of? So rather than keeping this n now, we can load n directly into the counter, but in this case the counter has to be a down counter. So now this is basically a down counter. Okay, so this down counter has to be loaded with n initially. So now what will be the other hardware? S anyway will be here. We will be having the adder, I and S will be added, the output will go back as usual to S. Now how about the control structure? Earlier the comparator that is used for the control structure, it is stopping the whole process after it completes. Now what should be the control structure? We have to look into the counter output. Because the n is no more here, we won't have to change that, but what will be that? We have to find out when it achieves 0. So whatever be the value of n, final value will be 0. So how do you detect a 0? If you simply use an OR gate, all the values are 0, then the output will be low. Okay, so if you use that as long as even one bit is non-zero, then it should operate. Then we should have, suppose it is 8 bit, then we should have some OR gate. So it is symbolically drawn like that, meaning that it is having, let us say, 8 bit or 16 bit as the case may be. So output of that one, the control signal is going to S, and so as long as it is high, they are being enabled. When it falls low, that is when I becomes 0, then their operation is inhibited. Okay. So now this will work perfectly. So if you look at this structure compared to the previous one, we have saved one register and one comparator at the cost of slightly increased complexity in the counter, because now it has to be a loadable counter. Earlier it will start maybe it is starting from 0, but now it should be a loadable down counter. So some structure will be more, but taken together the earlier counter and the register, you can say that it is more economic. Similarly, in case of the previous structure, there was a comparator, but now there is a single OR gate. So a typical comparator, if you go into the logic design, you find that there are several XOR gates and an OR gate of this, or maybe AND gate of this complexity. So there also you are reducing the complexity. So this one we will call modification, or rather optimization at the architectural level, where you are not making much change in the algorithm. You say, just one moment, if I show in the algorithm. So we are not changing the algorithm drastically. Changing the algorithm means we should have taken this one. So we are remaining within the scope of that, whatever is being supplied to us. And here we are making some minor changes which will not affect the final result. Okay. So that much we are doing over here. So now if we go into the third level, that is the logic level. From architecture we have to go to logic level. So how we go into the logic level? So let us think about, say, a 2-to-1 multiplexer. So are you aware what is a 2-to-1 multiplexer? It is just like a switch. So it is having two inputs. If we call them A, B, the output is Y, and there is a control signal, we may call it S. S generally stand for select line. So it is something like this, that Y will be equal to A if S is 0, Y will be equal to B if S is 1. So sometimes it is shown like this, that as if it is a switch controlled by this S. Okay. So if S is 0, it goes into this, if S is 1, it comes like this. But so far as the logical implementation is concerned, how do you implement this? It requires some AND gate, OR gate, etc. So it is something like this, the A we can go through, we can pass through an AND gate like this. So it will be passed if this is high, right? Otherwise it will remain low. Similarly, B also, if we are having another AND gate, if this is high, then B will be passed. So now if we put an OR gate over here, that it can either take this output or that output, whichever is true, and say this will be Y. So how do we fit S into this framework? So S, if it is high, then B will be allowed to reach here. Otherwise, if S is low, that means we should have something like this, an inverter over here. Then if S is low, this will become high. So just look at the logic. This is the so-called 2-to-1 multiplexer. So if S equal to 0, this is high. So now it will allow A to pass over here. Okay. So what is basically this Y? If I look at its logical expression, it will be A into S bar plus B into S. So that means if S is high, then B will be there at the output. Otherwise, if S bar is high, that means if S is low, then Y will be equal to A. Okay. So now if we look at the structure here, this we will call the design at the logic level, where we are talking about the gates. Okay. At the top level, possibly we will draw a black box like this, that it is having a functionality of 2-to-1 marks. Now here in this logical diagram, if we just try to calculate how much is its area, so how do you do it? Suppose now you require a little bit of knowledge at the transistor level, that if you translate it into a transistor level design, how many transistors will be required to have an inverter. So we already know how many transistors, 2. How many transistors for AND gate? It will be actually 6. I mean, if we look at the structure, then we find that inverter we have already seen. So if we look at this structure, 2 p type of transistor in parallel and 2 n transistors in series. So, I am not shorting them, it will look clumsy, otherwise the same signal A is given to one p transistor and one n transistor. Similarly, one transistor is getting B, another transistor at the p level, that is also getting the same variable B, and now this is the ground line. Here it is the output. So, we can generally say, though that is I mean sometimes not correct to infer, that if any signal say A is high, then n transistor will be on, p transistor will be off. If A is low, n transistor will be off, p transistor will be on. Okay. So, from that logic we find that if we look at A B, when both are high, then only Y is getting a path to ground. Okay. So, if we look at its truth table, we find that only when A and B both are high, at that time it is 0, otherwise if any one of them is 0, so it is not getting a path over here. Now we have to look that whether it gets a path over here. So, either if this is 0 or that one is 0 or both are 0, then Y is getting a path to VDD. So, in all other cases it will remain high. So, 0 0 0 1 or 1 0. So, what is this gate? This is just opposite of AND. So, it will be a NAND gate. So, a NAND gate that requires only 4 transistor. Okay. Now, if you follow the NAND with an inverter, then it will become an AND. So, NAND gate is 4, inverter is 2. So, 4 plus 2 is 6, that is for an AND gate. But you might argue that okay, why can't we have directly a realization of AND gate involving 4 transistors rather than having an inverter added to an AND. Okay. So, can we have a logical structure of transistors that will fetch us some functionality of an AND gate. So, if we go by that formula, that n transistor is becoming on whenever it is getting high. So, if I say it is VDD, our realization should be something of an AND gate, that is A, B, and if I say that this is Y. So, when both are high, at that time the output should be high, right. So, to have that one, can we have something like this, that 2 n transistors here, if we call them A and B, and now we say this is the output Y. So, when both are high, Y will be connected to VDD. Now, when any of them is low or both of them are low, so under that circumstance, if we put 2 p transistors over here, taking from A and B, then the output should be low. So, do you think it will work? It should, at least at the first thought. Okay. But what could be the real problem? That is, this is something like an N type transistor, right. So, N type transistor, when they will be able to work, when its gate is at a higher potential. So, higher means what is the potential? That is at VDD. So, if you look at the structure that we have seen for a MOS transistor, that it is something like this. So, now this is high voltage, the source, if you look at this structure, the source is also at high voltage. Okay, so, this is at high voltage, this is also at high voltage. So, there will not be much voltage to turn it on, because if there is no potential difference, it will not be able to turn on. The logic that we are saying, that whenever we are applying high, that will be on, that is true when the N is connected to ground at least in one side, but here this is connected to the VDD. So, what will happen, even initially the transistor might become on, but this point cannot go beyond VDD minus VT, VT being the threshold voltage of that MOS transistor. Threshold is the minimum voltage that you require to overcome the work function. Before that, the channel will not be established. Okay. So, what will happen, if you really use this, you will find that the transistors are not remaining on when the output is going towards VDD. Maybe if VDD is 5 volt, you can find that Y is at most 4 volt if the threshold voltage is 0.5 volt for each of them. So, you are compromising the noise margin. I think you know what is the noise margin. Noise margin is something that is the main advantage of the digital, that even if the noise is there, in the presence of noise you can distinguish between two distinct logic levels 0 and 1. But if you say that the output logic level 1 you are compromising, then obviously that beauty is lost and we are compromising the logic reliability. So, this is not done, that NMOS is never put in the top side, always it is put on the ground side, so that we can apply that logic and the transistor really becomes totally on. So, that is why it will require 6 transistors. So, we always should have some realization where it will be like this. So, for a NAND gate, what is the logic? It is AB bar. So, bar means when this portion is becoming true, the output will become false. So, that will be true if it is connected to the ground line, then only the output can become false. False means output should be 0, and when that, I mean whatever is involved over here, that is becoming true. So, for N type to be true, they should be high. Okay, so it should be always some sort of complementary form. Okay, so NOR gate also will be something very much similar. So, what will be the structure of the NOR gate? If you look at the NOR gate, rather than having parallel transistors here and transistors, the N transistor in series, it will be just having a complementary topology. So, we will be having 2 P transistors in series and N transistors in parallel. So, what is the logic? When any of A or B they are high, then if this is the output, that will become low. Okay. So, if we look at its truth table, so for either of the first 3 cases, the output will be if it is both are 0, then only it will not get any path to the ground. So, only in that case it will get a path to VDD. For any other cases, when either A is high or B is high, it will get a path to ground. So, then it will become this. So, what is this logic? This is just opposite of OR. In case of OR, this will remain 0, everyone else will become high. So, this will be something like a NOR gate. Okay. So, now using this idea, we can compute what is the total cost of this. So, what will be the total cost now? AND is 6, OR is 6. So, the total number of transistors will be 20. Okay. But there is a rule called De Morgan's theorem. Maybe those of you are having that one in your class 2 courses, you are aware of that. So, what it says, this is something like A plus B plus C whole bar, it is equivalent to A bar into C bar into something like this. Okay. So, if we think of this one, that De Morgan's theorem, then as we understand that this type of structure is costlier because we are using AND OR rather than NAND and NOR. So, if we can convert them into some equivalent NAND type of structure, then how will it look like? Suppose we want to make this AND gate converted into a NAND, but logic should be same, right? We should not change the expression. So, if we make this a NAND gate, the output of that one should be inverted once again, so that the overall logic won't change. I am not drawing the left hand side part. So, here also this one I am changing to NAND gate. So, the output of this one should also be inverted before feeding it to the next block OR. So, now if I look into this one and apply De Morgan's theorem, so what it says, this is an OR gate. Okay, so this is basically getting A bar and B bar and ORing that one. So, that is basically if I take something like this, A bar and B bar and ORing. So, just an opposite or of that one will be something like this. I can say that A bar plus B bar plus C bar, that is equivalent to A, B, C, etc. whole bar, right. So, now this gate, this can be replaced by a NAND gate. Okay. So this is already a NAND gate, that is 4 unit, this is another NAND, and this will finally become a NAND gate. So it will also cost 4 transistors, and there is an inverter which cost 2 more transistors. Okay. So at the logic level, just by applying De Morgan's theorem, we can reduce the number of transistors from 20 to how much? 14. So 30% direct savings, okay, that we can have. Now, so far whatever we are talking about logic level, but finally we have to implement that in transistor level. Okay, so we have to think of how you do that in transistor. Now we see, if we stop at gate level, that we cannot see what is inside a gate, we cannot modify the internal structure of a gate, then how do we proceed? Suppose we are having some problem where we are encountering a logical expression which looks like this. Suppose y equal to AB plus C whole bar. So can we compute what will be the number of transistors required in realizing this? So how do you go about this? So first of all, we have to draw the gate level diagram. Okay. So we have already learned that if we used something like a complementary logic, that is AND, NAND, NOR rather than AND OR, then it will be beneficial for us. So from that point of view, can we find out that, okay, what will be the most economic implementation of this? Let us try a simple implementation without looking for any sort of optimization. That will be how much? AB we require an AND gate, okay, and then a NOR gate. 6 plus 4, 10. So can we reduce the number from 10? If we use, say, some other structure, say De Morgan's theorem, etc., do you think it is possible? So y equal to AB plus C whole bar. Okay, so even if you change that, you will find that in some place it will be once again complementary logic, in some place it is uncomplemented logic. So maybe the number you can reduce at most to 2 transistors. I mean, so initially how many you said? 10. So maybe at most you can achieve 8, not less than that. Okay, but if you think about the transistor level realization of this, first of all, what it means in terms of truth table, when the output will become low, can you identify that? So in words, if we say the output will become low if A and B both are high or C is high. Okay, so if you think about that, and from that logic we will try to synthesize the circuit, that this is the output Y, this is the ground line, Y should be connected to the ground line if A and B both are high. So then I can think of 2 transistors here, one is connected to A, another is connected to B. So this portion is satisfied. Or it says even if C is high, then also the output should be low irrespective of the value of A and B. So how do you implement that then? Make a parallel connection here, C. So that takes care of this output being low. But under all other conditions, suppose say A and B neither they are both high nor C is high. At that time it has to be high, the output should be high, it should not be low, it should be high. So if we just keep like this, then what will happen? If this is not satisfied, output will become floating, which is not desirable at all. So for all other combination, the output should be tied to VDD. So how to do that? First of all, what it says, that if C is high unconditionally, unconditionally means without depending on A and B, this should be low. So if C is high, this should be low. Now at the same time, we should ensure that if C is high, it should not get a path to VDD. So how do you ensure that? Then maybe there is a series path we can think of, that if we put C like this, then if C is high, a P transistor will become off. Okay. Now what about the other case? Suppose C is low. So C is low means this path is off, but this path is on. Okay. But now A and B both are high, then also it should not be taken to VDD. Okay. So how do you make two parallel combination of A and B? This will be P type anyway. So this is just a complementary topology of this. Here A and B are in series, here A and B are in parallel, here C is in parallel to the combination of A and B, here C is in series with the combination of A and B. So this always ensures that for all combinations, all possible combination, the Y is either connected to ground or it is connected to VDD. There will not be any case, any floating situation where Y is neither connected to VDD nor it is connected to ground. Okay, so now here how many transistors you are using? Only 6 transistors. So if you go into a transistor level realization, then you can see that how you can reduce the number of transistors and eventually the total area. And if the number of transistors are less, obviously the overall power consumption will be also less, because otherwise if you have used one AND gate followed by another NOR gate, then each of them will consume independently the power. Okay. But now this is a very compact circuit, CMOS circuit, by which you can realize the same one. So this we will call optimization at the circuit level. Okay. So now you see what is the impact over here. If you do something like this, and if you are having several such logical expressions, then saving a small amount here may be actually translated into a very large value, particularly if you are using the same structure repeatedly. So that typically happens when you are designing an adder, so to say, because addition is an ubiquitous operation. So everywhere, whether it is multiplication, square root or anything else, at that time you are using something like a little less number of transistors. Suppose in your design there are 10,000 multipliers or 10,000 adders. So if you can save just 2 transistors, then it will be multiplied by that factor. Okay. So though sometimes it is apparent or it is thought that if you can do something at the algorithmic level, then only you can have much more economic operation. That is not always true. Every level is having its own significance, and whatever you are doing at the top level, obviously it is having very great significance, but you cannot neglect the savings that you can do at the lower level, because whenever you are bringing it up, it is getting multiplied by a huge factor. Okay. And obviously device design, etc., they are also having its own advantage. So now at this point, if you are having any question, or we will go for a slightly more complex design then. Have any question so far? I mean, whatever. Yes.
Can we predict in any way the transistor level optimization from the logic level?
For some obvious structure, it is straightforward, but sometimes what happens, if the structure itself is not known. Not known means this type of structure, whatever I have shown, it is called a static CMOS logic, where the translation is straightforward. Just by having this expression, you can automate even this design. You can write a program specifying that, okay, if you find something like this expression, how to I mean arrange these transistors over here. But there are, I mean, many other class where the topology is something different. Now first of all, you have to choose that which is the actual topology you will be using. Okay, so there are several factors, I mean, starting from speed, power and area. So actually we are going to discuss that. So the major issues that we are going for look into this, one is speed, that we have already discussed, that it depends primarily on the critical path. So if you are designing an adder, how fast the adder works, that decides the maximum speed. So if you can design at the logic level also, for example, if we just take the previous example, this logic, if you have used it something like this, that AND followed by, let us say, a NOR, then AND gate is having some delay, then NOR gate is having some additional delay. So from A, B, C or the inputs to output, the delay will be approximately 2 gate delays. But if you are using a structure like this will be just identical to a 3 input gate delay or even less in some cases. For example, in this case it is actually less because the delay, as we have already discussed, it depends primarily on the charging and discharging path. So in this case, what is the worst case? That is when it has to discharge with A and B, then 2 transistors in series. So 2 series resistance are coming into the picture. Here also, though it is a 3 variable function, but here also the maximum level of transistors that it has to encounter will be 2. So unlike a 3 input gate where 3 transistor either on top or at the bottom will be in series, if you think of 3 input NAND gate or NOR gate, it is even faster than that. Okay. So if you can think of that speed at the logic level, then also when whatever we have discussed so far in terms of area, but in terms of speed also you are having some sort of advantage. So other than speed, you are also having another concern, that is area, because particularly for some commercial houses producing those ICs, the area is very important because area decides the cost of the chip. On one single wafer, how many transistors they can, how many chips they can make. If they can increase the number, then obviously their production cost will be less per chip. And third one, which has attained enormous impact nowadays, that is power. Particularly with all these portable devices, people don't want to change the battery or charge the battery very often. So if you can design a circuit that consumes lower power, that is another issue nowadays. And for different applications, you require different weightage of them. For example, if you require something like a video communicator, then you require high speed, otherwise what will happen, the picture will be jerky, okay, you will be having some annoying effect. At the same time, maybe area is a factor, you don't want to have a very large area chip, and power is also there, but maybe for that particular application speed is having the maximum importance. So whenever you are trying to find out a cost function, speed will figure out in the having more weightage over there. But in some other case, say biomedical implantable device, where you want to have a battery which will be inside the body for the whole lifetime, so their power is of much concern. And maybe where you are implanting that, how much space is there, depending on that, area might be also of concern, but speed might be possibly of little concern there. Okay, if it is a pacemaker or some other telemetric device, then speed might be very low, but in that case power and area, they might be of concern. Okay, so depending on the application, your concern might be different. Now, as we have discussed that if we can design, let us say at logic level, just think about a problem that you are having 2 input AND gates, using them you have to make 4 input AND gates, okay, and functionality. So how do you go with your design? You will be putting 3 2 input AND gates to form such a structure. Now it will act as 4 input AND gate, right? Now suppose some of your friend is saying that, okay, I am having another design which looks like this. So do you think functionally this will work as 4 input AND gate? Answer is yes. Okay. Now if you compare these two structure, which one is better? Why? Yes. So first one, it appears that, okay, the delay from the input to the output, that is only having 2 levels of delay. So if one AND gate delay is 0.1 nanosecond, the overall delay is 0.2 nanosecond here. Here it is 0.3 nanosecond, 3 AND gate delays. Okay. But if you think about the whole structure of your design, then if it is not in the part of the critical path, we have already defined what is a critical path, that is the longest chain of the combinatorial logic that decides the maximum clock speed. So if it is not the part of the critical path, so whether you are using this one or that one, that is not really going to affect your system speed. That is the first design, that is the first observation. But still, if I say that you use this design, possibly something is pinching you, that this design is really not efficient, that maybe if you can redesign your critical path, if it falls below 0.3 nanosecond, then this one will become critical path, right? But this one is really having a little advantage. What is that? If you think about this structure, I mean, where it can be useful, suppose you are using a counter, 4-bit counter. Okay, so counter started from 0000, and now all the bits are changing. So first LSB will change, then next bit will change, and so on. It will go on like this. So finally, all the bits will be high. So suppose you want to check when the counter is reaching its maximum value. Okay, so this ABCD, if you use it over here, then the output will become high only when all are high, right? Now, if you look at the power consumption of the first circuit, suppose if I say this is A, this is B, this is C, this is D. If I look at this output, that node, how many times it will become 1? 3 times before becoming 1 finally. So once it will become high here, okay. Once again when this CD combination is 0 1, at that time also it will be 1 and 1. Once again sometimes this DC combination is 1 and 0, at that time also it will be 1 1. Finally when this is all are 1, then only the final output will become high, but otherwise in all these cases it will become high. So it will become high 4 times, though it is not contributing to the final output change, and whenever there is a change it consumes some power. Why? Because that load capacitance, whatever we have discussed, it will be charged up. Once again when it becomes 0 in the next cycle, it will be discharged. So unnecessarily it is consuming power, okay, though the actual output is not changing. If output changes, obviously you have to burn some power, but it is not contributing to that. Now if you use this, what will happen to this point? The same thing, though the output is not changing, it is changing, so it will burn some power. But if you can change the order, that rather than putting ABCD in this way, if you put A here, B here, C here, D here, then what will be the situation? Because A is changing many times, but unless this input is 1, the output will not change. Okay, so now this was changing 4 times, or rather 8 times I think, here it will not change. So C and D, this will be high only in the last part. So when it enters the last quarter of the operation, then only it will become high, and it will be high, I mean it will remain high till you are having the final output high. It will not switch between zeros and 1 unnecessarily. Similarly, when B will also become high in the last but one step I think. So now it will become high, and in the last step when A is becoming high, at that time it will become high. So from power point of view, this is actually superior, this is consuming much lower power. So if it is not part of the critical path, then nowadays we prefer this structure. Though maybe 15 years back or 20 years back we used to find out that we are having an inclination of using this one, saying that it is having less propagation delay. So now the philosophy of design, that is changing. So this is something we can do to save power. At what level? Whatever we have been discussing, can we identify at what level we are talking? That is logic level. Gate level means it is basically logic level. Now at different level, say at transistor level also, you can think of saving some power. Even at the architectural level, whenever you are reducing the total number of operation, that means you are saving power, because if you can save some computation, you can save some power which will be otherwise burned for computing those things. Okay. At the architectural level, whenever you are saving some register or counter or something, at that time also you are saving some power. Okay. So maybe we can think of some other structure, say memory and all, but I think maybe you are not yet exposed to memory structures, etc. So just memory as a functional block, if we think of, it is something like this, that if I think about a particular page having several lines, and in every line I can write something. Okay. So maybe if you can think of a line, I can write 8 bits over here. So functionally this is equivalent to having 8 flip-flops, though the structure is somewhat different, and I can have some address lines by which I can refer to a specific line of content. Suppose say there are 256 such lines, then how many unique address I should have to identify those 256. So, in how many bits I can encode? 8 bit. Okay. So, I will call that line, I mean those lines, the address line which are carrying 8 conductors having information about the lines. Okay. So, if it is all 0, maybe it is actually pointing to the first line. If it is 0 0 0 and only the LSB is 1, it is the next one, and if it is all 1, let us say it is indicating the last line. Okay. So, in that way generally a digital processor, whenever it gathers data, it stores all the data in a memory like this, that it addresses the first location, whatever the data is coming it stores over here, then the next data it is storing over here, next data is storing over here. So, effectively we are having some counter here that counts from this 0 0 0 0 etc. to all ones. Okay. So, if it is 8 bit, we start with 8 0 and gradually we will reach to 8 ones. Okay. So, now whenever the counter outputs are changing, as we have seen that any change means power consumption, because capacitors are getting charged and eventually getting discharged. So, if we look at the address pattern, how it looks like, suppose 8 zeros to start with, then in the next instant 1 bit is changing. So, number of changes 1. In the next change, this is changing to 1, this is becoming 0. So, how many bits are changing? 2. This bit is changing from 1 to 0, this is changing from 0 to 1. Okay. In the next one, only 1 bit is changing. In the next, 3 bits are changing. Okay. So, in that way, if you tabulate, you will find that there are many changes like this if you sum total in all these 256. Okay. One way to save this is, rather than using a simple binary counter, if you use something like a gray counter. You know what is a gray code? In a gray code, what is the speciality of a gray code? Every step only 1 bit is changing from its previous value. So, that means here we won't be having figures like 2, 3, or in I mean whenever we go for subsequent structure, say you can think of this one. So, how many bits are changing at that point? All the 8 bits are changing. Okay. So, in gray code they will be all replaced by 1. So, if we want to fill up this memory with some input data by using a counter, so rather than using a binary counter, use a gray counter. But what will be the possible change? If you use 0 0, the first data will be stored here, the second data will be stored here. If it is gray code, rather than having 1 0, what will be the next value? 1 1. So, maybe it is pointing to that third data will be stored here, fourth data will be stored here. But that does not matter, because whenever you will be fetching, once again if you use gray counter, it will be fetched from this data first, this, and then it will come here and then it will go there. So, it will be transparent to the user. Okay. So, here you can save some power at the architectural level itself. We are not going into the logic design, we are neither going into the transistor level design, and actually the low power design, I mean people are having a lot to do at the device level, because the device leakage, if that can be reduced, because nowadays device leakage is contributing to a very large component of power loss. In earlier days the circuit power loss, that is more, because the capacitors were very large, that capacitor being charged and discharged compared to the others loss. But nowadays with the shrinkage of the dimension of the devices, the capacitors are becoming smaller and smaller. Okay, the resistance are also becoming smaller and smaller. So, finally we find that the leakage is nowadays becoming comparable to the operational speed, I mean operational power loss. Okay. So, I think this is what I feel is just a very incomplete sort of discussion whatever we have made, but at this level I think that is once again something like an optimum. So, now I think you are having so many literatures available that in whichever direction you think of, if you pick up algorithm or architecture, logic, circuit, device, every level it is possible to do a drastic reduction of say this power, or to gain, let us say, speed, reduce the area. Okay. So, if you are having any question offline also I am available. Okay. So, let us conclude the discussion here. Thank you.